Welcome to this coding problem walkthrough. Today, we'll dive into problem number 320, Generalized Abbreviation. In this problem, we'll explore how to generate all possible abbreviations for a given word using various approaches, including a brute force method. Let's get started. In this problem, you are given a string called word, and your task is to generate all of its generalized abbreviations. A generalized abbreviation is created by replacing parts of the word with their corresponding lengths, while keeping the remaining characters in their original positions. For example, if the input word is word, one possible abbreviation is W1 or 1, where the O is replaced by its length, which is 1, and the D is also replaced by its length, which is 1. Your goal is to return all such abbreviations in any order. The input is a single string consisting of lowercase English letters, and the output is a list of strings, where each string represents a valid abbreviation of the word. The output will include all valid generalized abbreviations of the word. For example, if the input is word, the output might look like this: 4, 3D, 2 or 1, 2RD, 102, 101D, 1 or 1, 1ORD, W3, W2D, W1 or 1, W1RD, W2, W1D, W1, word. Here are some examples of how these abbreviations are formed. 4 replaces the entire word with its length, which is 4. 3D replaces the substring war with its length, which is 3, and keeps the D. 102 keeps the W, replaces OR with its length of 2, and keeps the D. Finally, word represents no abbreviation, where the word remains unchanged. These abbreviations are generated systematically by replacing different substrings with their lengths. For shorter words, the process is simpler. For example, if the input word is a, there are only two possible abbreviations. The first is 1, where the single character a is replaced by its length, which is 1. The second is a, where no abbreviation is applied, and the word remains unchanged. Similarly, for the input ab, the output would be 2, 1b, a1, ab. Here, 2 replaces the entire word with its length of 2. 1b replaces the a with its length of 1 and keeps the b. A1 keeps the a and replaces the b with its length of 1. Lastly, ab leaves the word as is, with no abbreviation applied. The constraints of the problem specify that the length of the input word can range from 1 to 15, and the word will only contain lowercase English letters. There are a few edge cases to consider. For the shortest word, such as a, there are only 2 possible abbreviations, as we just discussed. For the longest word of length 15, the number of possible abbreviations increases significantly, making it computationally challenging. Additionally, if no characters are replaced, the abbreviation is simply the word itself. It's also important to note that abbreviations can overlap. For example, word can be abbreviated as 2RD, where W is replaced by its length of 2. Finally, the order of the abbreviations in the output does not matter, as long as all valid abbreviations are included. To tackle the problem of generating all possible abbreviations for a given word, several approaches can be considered. The brute force approach, for instance, involves generating every single combination of abbreviations. Here, each character in the word has 2 options: either keep it as is or replace it with a count that represents the size of the substring it abbreviates. This results in 2 raised to the power of n combinations for a word of length n, as every character contributes to a binary decision. To implement this, recursion or backtracking can be used to systematically explore all possibilities by deciding at each step whether to abbreviate or retain the current character. However, while this method is simple and intuitive, it's computationally expensive. Its time complexity is exponential, 2 to the power of n, due to the large number of combinations, and it also requires n space for the recursion stack, making it impractical for longer words. Another approach, backtracking with optimization, addresses these inefficiencies by systematically exploring paths while dynamically building the abbreviation string. This avoids redundant computations and improves efficiency over brute force methods. The key to optimizing backtracking lies in how we handle consecutive abbreviations. Instead of generating intermediate strings like 1ORD or W1RD, we can simplify the process by appending the count of abbreviated characters directly. For example, if 1 character is abbreviated, we append 1 to the result, and if 2 characters are abbreviated consecutively, we append 2 instead. This avoids unnecessary string manipulations and ensures we systematically cover all valid abbreviations with minimal overhead. This approach is still exponential in time complexity, 2 to the power of n, since we explore all possible combinations, but it eliminates redundant operations, making it much more efficient than brute force. Additionally, it only requires n space for the recursion stack depth. An alternative to recursion is the iterative bitmask approach. Here, we treat the problem as a bitmasking operation, where each bit in a number represents whether the corresponding character in the word is abbreviated or kept. By iterating over all integers from 0 to 2 to the power of n1, we construct abbreviations based on the bitmask. Consecutive bits set to 1 are grouped and replaced by their count, which avoids the need for recursive calls and offers a non-recursive, systematic way to generate abbreviations. Despite the differences in implementation, both backtracking with optimization and iterative bitmasking share the same time and space complexities. The time complexity remains 2 to the power of n, because we must generate all possible combinations of abbreviations, and the space complexity is n, which accounts for storing the current abbreviation string or recursion stack depth. Among these methods, we choose backtracking with optimization as our preferred strategy. It is not only efficient but also intuitive, thanks to its recursive nature. The flexibility of recursion allows for cleaner code and simplifies the handling of edge cases, such as grouping consecutive abbreviations into counts. This makes the implementation easier to debug and extend for variations of the problem. The iterative bitmasking approach, while elegant and non-recursive, requires additional care when dealing with consecutive counts, which can complicate the code unnecessarily. When comparing these approaches, each has its own trade-offs. The brute force method is conceptually simple but inefficient for larger inputs because of its redundant operations, making it impractical for real-world use. Backtracking with optimization, on the other hand, strikes a balance between simplicity and efficiency. It avoids unnecessary computations and is highly extensible, making it a versatile solution for problems of this nature. The iterative bitmasking approach is a non-recursive alternative, offering a clean and systematic way to generate abbreviations, but its need for careful handling of consecutive counts can increase implementation complexity. By selecting the backtracking with optimization approach, we achieve a good balance between performance and code clarity. It leverages the power of recursion to dynamically generate results, handles all edge cases effectively, and remains easy to understand and maintain, making it the most practical choice for this problem. To begin, this problem involves generating all possible abbreviations of a given string by replacing substrings of characters with their lengths. For example, if the word is word, valid abbreviations include the original word, as well as variations like W1RD, W2D, 102, and so on. The key here is to understand that each character in the word has two choices: it can either remain as it is, or it can be replaced with an integer representing the length of an abbreviated substring. Because of these two possibilities for each character, a word of length n will have two n combinations. To solve this, we'll use a recursive backtracking approach. This method will allow us to systematically explore all possible states of abbreviation, and will keep track of our progress in a results list where all abbreviations will be stored for final output. Let's break this process into clear, manageable steps, starting with initializing the input word and preparing for recursion. Now, let's dive into the recursive backtracking step. Recursion is a natural fit here because it lets us make decisions at each character of the word. For each character, we have two choices: we can either include it as a literal character in the abbreviation, or we can abbreviate it by skipping the character and incrementing a counter to track the length of the abbreviated substring. To implement this, we start at the very first character of the word. If we choose to abbreviate a character, we increase the counter. If we decide to keep it literal, we append the current counter value, if non-zero, followed by the character itself to the current result. We then move to the next character and repeat the process until we reach the end of the word. The base case occurs when the recursion reaches the end of the word. At this point, we finalize the current abbreviation by appending any remaining counter value and then store the result in our list of abbreviations. Next, we ensure that all possible paths are explored by backtracking. This toggling between keeping a character literal and abbreviating it is what allows us to generate all two n combinations. To visualize this, think of the recursive process as constructing a decision tree. Each node in the tree represents a decision either to abbreviate or to keep a character literal. The depth of the tree corresponds to the length of the word, and the leaves of the tree represent the final abbreviations. One key optimization here is the use of a counter for abbreviations. Instead of explicitly building substrings, we simply track the length of the abbreviation using the counter. This makes the algorithm more efficient and avoids unnecessary string manipulations. When we reach the base case, appending the counter ensures that even partially abbreviated paths are correctly finalized before being added to the results list. When we consider efficiency, it's important to note that this algorithm is inherently limited by the need to generate all possible abbreviations, which is 2n. Therefore, the time complexity is proportional to the total number of combinations, which is 2n, multiplied by the time it takes to construct each abbreviation, which is O(n). This gives us a total time complexity of O(n*2 to the power of n. On the space side, the recursion depth is O(n), as we process one character at a time. Additionally, the results list requires O(2 to the power of n) space to store all generated abbreviations. Combined, the overall space complexity is O(n+2 to the power of n). To implement this efficiently, we use three key data structures: a string to represent the current abbreviation being built, an integer counter to track the length of the current abbreviation, and a list to store all final results. Analyzing the complexity further, the time complexity is driven by the exponential growth of the combinations, 2n, as every character has two possibilities. Since constructing each abbreviation takes O(n) time, the total time complexity is O(n*2 to the power of n). The space complexity includes both the recursion stack, which is O(n), and the results list, which stores all abbreviations and requires O(2 to the power of n) space. Together, this gives us a space complexity of O(n+2 to the power of n). While this might seem costly, it's important to understand that generating all combinations inherently requires this amount of computation and storage. The algorithm is designed to manage this efficiently by leveraging recursion and avoiding redundant operations. Let's walk through an example. Consider the input word ABC. We begin with an empty abbreviation and start at index 0. At each step, we choose whether to keep the current character literal or to abbreviate it. At the first level, we decide between including a or abbreviating it to 1. At the second level, for each of these choices, we decide between including B or abbreviating it. Finally, at the third level, we make the same decision for C. This recursive process builds a tree where each path represents a unique abbreviation. The results of this process for ABC would include ABC, AB1, 1C, A2, 1BC, 1B1, 2C, and 3. Each abbreviation corresponds to a unique path through the decision tree, demonstrating how the algorithm systematically explores all possibilities. It's important to consider edge cases to ensure the algorithm handles all scenarios correctly. For an empty input string, the only possible output is an empty abbreviation. For a single character input, such as the output would be A1, representing the literal and abbreviated forms. Another edge case is when all characters are abbreviated. For a word of length n, this would result in a single abbreviation consisting of the number n. To optimize further, using a counter to track the length of abbreviations minimizes unnecessary string operations, and the recursive structure ensures that all combinations are explored systematically without redundant computations. These optimizations make the algorithm both robust and efficient, even for challenging edge cases. This Python implementation solves the LeetCode problem number 320, Generalized Abbreviation, using a backtracking approach. Let's break it down. The generate abbreviations function begins by defining an empty list, result, which will store all the possible abbreviations for the input string word. A helper function backtrack is then defined inside it. This function takes three arguments: index, the current position in the string, current, the current abbreviation being built, and count, the count of consecutive characters being abbreviated. The base case of the backtrack function checks if index has reached the end of the string. If so, any remaining count, representing abbreviated characters, is appended to current, and the resulting abbreviation is added to the result list. The recursive logic has two branches. 1. The first branch abbreviates the current character by incrementing the count and moving to the next index. 2. The second branch keeps the current character literal. If there is an ongoing count, it converts the count to a string and appends it to current, then appends the actual character and resets the count to 0. The backtrack function is initially called with an empty string for current, 0 for count, and starting at index 0. Upon completion, the result list contains all valid abbreviations. This approach ensures all combinations of abbreviations are explored, with a time complexity of O(2 to the power of n), due to the binary branching at each character. The function efficiently handles edge cases such as empty strings and long inputs by leveraging its recursive structure and count tracking. Here, we are implementing the solution to generate all possible generalized abbreviations of a given word. The core of our approach is a backtracking method. We start by defining a public method called generate abbreviations that takes the input word as a string. This method initializes a result list to store all the abbreviations and invokes the backtrack helper function. Now, the backtrack function is the heart of our solution. It takes 5 parameters: the original word, the current index in the word, the current state of the abbreviation being built, a count representing consecutive abbreviated characters, and the result list to store generated abbreviations. The first thing we check inside the backtrack method is whether the current index has reached the end of the word. If it has, we finalize the current abbreviation by appending the count, if it's greater than 0, and then add the resulting string to the result list. This serves as our base case for the recursion. Next, we handle the 2 main recursive decisions. The first decision is to abbreviate the current character by incrementing the count and moving to the next index. This effectively skips the current character in the abbreviation. The second decision is to include the current character in the abbreviation. Before doing so, we check if there's a non-zero count. If there is, we append it to the current abbreviation string to represent the skipped characters. Then, we add the actual character at the current index and reset the count to 0 before proceeding to the next index. By exploring these 2 paths for every character in the word, we generate all possible combinations of abbreviations, ensuring we cover every scenario. Finally, when all recursive calls are complete, the generate abbreviations method returns the result list containing all the generated abbreviations. To solve this problem, we use a backtracking approach to explore all possible abbreviations of a given word. Starting with the input word, the initial call to our backtrack function sets the index to 0, the current string to an empty string, and the count to 0. At each step, we have 2 choices: we can either abbreviate the current character, which increments the count, or we can keep the character as is. For example, on the abbreviation path, we skip the character W at index 0, increment the count, and make a recursive call to explore further. This process continues, abbreviating each subsequent character until we reach the end of the string. At that point, the accumulated count, which represents the number of skipped characters, is appended to the current string, resulting in the abbreviation 4. On the non-abbreviation path, we keep the character W at index 0 and proceed recursively with the same 2 choices for the next character. This systematic exploration ensures that we generate all possible combinations of abbreviating or keeping the characters in the string. As we explore all possible paths, we generate a range of intermediate outputs, such as 4, 3D, 2 or 1, and 2RD. These represent different combinations of abbreviations and kept characters, like skipping all characters, skipping all but the last, or keeping specific characters while abbreviating others. By continuing this process for every possible path, we end up with the complete set of outputs: 4, 3D, 2 or 1, 2RD, 102, 101D, 1 or 1, 1ORD, W3, W2D, W1 or 1, W1RD, W2, W1D, WAR1, word. This set includes all valid abbreviations of the word. Now, consider a simpler example where the input is just a. Here, the initial call to backtrack starts with the same parameters: index 0, an empty current string, and a count of 0. At this point, we have 2 choices again: abbreviate the character or keep it. If we choose to abbreviate, the count increments to 1, and since we've reached the end of the string, we append the count to the current string, producing the result 1. On the non-abbreviation path for the input a, we choose to keep the character in the current string, resulting in a recursive call with the current string updated to a when the count reset to 0. At this point, since we've reached the end of the string, we append the current string directly to the results. This gives us the second output, a. Combining the abbreviation and non-abbreviation paths for this input, the final output is 1, a. Now, looking at a slightly more complex example with the input ab, the process begins similarly with an initial backtrack call using index 0, an empty current string, and a count of 0. Again, we have the option to abbreviate or keep the first character, a. Choosing the abbreviation path increments the count and leads to further recursive calls to process the next character, b. Here, we can either continue abbreviating, which increments the count again and gives 2, or we can keep b, appending the current count to the string, resulting in 1b. On the non-abbreviation path for the input ab, we keep the character at in the current string and proceed to explore the options for the second character, b. Abbreviating b appends the count to the current string, resulting in a1, while keeping b appends it directly, resulting in ab. These two paths complete the exploration for this input, and when combined with the results from the abbreviation path, we get the final output, 2, 1b, a1, ab. By systematically applying this backtracking approach, we ensure that every possible abbreviation and non-abbreviation combination is captured for any given input string. To analyze the time complexity of this problem, we start by understanding the recursive nature of the solution. At each character in the input word, we have two choices: to abbreviate the character or to include it as is. This creates a binary decision tree, where each level represents a character in the word. For a word of length n, this results in a total of 2 to the power of n combinations, corresponding to the number of recursive calls. In each recursive call, we perform constant work, such as updating the current string with either a count or a character, which takes 1 time. When we reach the base case, where the entire word has been processed, we append the generated abbreviation to the results list. This appending operation scales with the length of the generated string, which can be at most n. Therefore, the total time complexity is influenced by both the exponential number of recursive calls and the linear work done in each call. Combining these factors, the final time complexity of the algorithm is 2 to the power of n asterisk n. The 2 to the power of n factor represents the number of recursive calls, while the n factor accounts for the work required to generate and store each abbreviation. Now, looking at space complexity, the recursive call stack contributes n space, as the depth of the recursion tree corresponds to the length of the word. Additionally, the result list, which stores all possible abbreviations, requires space proportional to the number of abbreviations. Since there are 2 to the power of n abbreviations, each with a maximum length of n, the result list consumes 2 to the power of n asterisk n space. Lastly, we use a few auxiliary variables, such as the current string and a counter, but their space usage is negligible compared to the call stack and result list. When we combine these considerations, the overall space complexity is 2 to the power of n asterisk n, with the result list dominating the recursive call stack's n contribution. Comparing this to a brute force approach highlights the efficiency of the optimized backtracking method. In a brute force approach, we would generate all possible strings of length n, mixing characters and numbers, and then validate each string to filter out invalid abbreviations. This would involve a significantly larger search space, roughly n asterisk 3 to the power of n, as each position would have 3 options: keeping the character, replacing it with a number, or doing nothing. In contrast, the backtracking approach directly enforces abbreviation rules during recursion, drastically reducing the search space to exactly 2 to the power of n valid abbreviations, making it far more computationally efficient. To solidify this understanding, consider the mathematical proof behind the complexity. The binary decision tree inherently leads to 2 to the power of n combinations, as each character in the word contributes 2 independent choices. Additionally, generating each abbreviation requires concatenating counts and appending characters, which can take n operations in the worst case. Combining these factors, the total time complexity is 2 to the power of n asterisk n. Meanwhile, the space complexity is dominated by the result list, which stores all abbreviations and requires 2 to the power of n asterisk n space. The recursive call stack adds an additional n, but this is asymptotically insignificant compared to the storage requirements. This analysis confirms that the backtracking approach is both time-efficient and space-efficient compared to brute force methods. When solving the generalized abbreviation problem, there are a few common pitfalls to watch out for. First, it's crucial to consider all possible abbreviations. For example, abbreviating the entire word, like word becoming for, or partially, such as would to, must not be overlooked. Missing these cases can lead to incomplete solutions. Another issue is incorrectly handling consecutive abbreviations. Abbreviations like W12D are invalid because the numbers cannot appear consecutively. You must ensure proper formatting in your implementation. Additionally, recursive backtracking can be inefficient if not optimized. Failing to prune unnecessary recursion paths will waste time and resources, so look for opportunities to break out of recursion early. Edge cases are another area where mistakes often occur. For instance, handling an empty string or single character words like a requires explicit handling to avoid errors. Finally, input size constraints for longer words, such as 20 characters, demand attention. Without optimizations, generating all possible abbreviations can lead to exponential time complexity, resulting in timeouts. This problem is frequently used in interviews to assess your grasp of recursion, backtracking, and even bit manipulation. The key is being able to identify when to generate all combinations and when to eliminate unnecessary paths. Problems like this often share patterns with other string transformation or combinatorial problems, so becoming familiar with recursive and bit masking strategies will pay off. Optimization is another critical focus during interviews. Demonstrating pruning techniques within recursion and discussing the trade-offs between brute force and more efficient approaches can set your solution apart. Additionally, interviewers frequently test your ability to handle edge cases, such as empty strings or extremely short or long inputs. Proactively addressing edge cases in your explanation can leave a strong impression. This problem shares similarities with several other LeetCode problems. For instance, LeetCode 78, subsets, uses a similar recursive backtracking pattern to generate all subsets of a list. Another example is LeetCode 22, generate parentheses, which focuses on recursively generating valid string combinations. LeetCode 784, letter case permutation, involves toggling letter cases to generate all permutations, a concept closely related to abbreviation problems. When considering how to approach these problems, recursive backtracking is often the go-to method. It's intuitive and straightforward for generating combinations, but it comes with exponential time complexity, making it less efficient for larger inputs unless you implement pruning. Alternatively, bit manipulation can provide a more space-efficient solution by representing inclusion or exclusion of characters, but it's harder to write and debug compared to recursion. Iterative generation is another approach to solving problems like this. It avoids the recursion stack, which can be beneficial, and it's often easier to debug. However, it tends to be more verbose and less intuitive, especially for combinatorial problems. Dynamic programming, while less common for problems explicitly requiring all combinations, can sometimes optimize certain variants of string transformation problems. That said, it's generally overkill for this type of task since it's not designed for enumerating all possible outputs. Choosing the right approach depends on balancing simplicity, efficiency, and the specific requirements of the problem. Great work! We've covered problem number 320, generalized abbreviation, including the brute force approach and key concepts. Remember, practice makes perfect. Be sure to try similar problems to strengthen your skills. Thank you for watching, see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!